Hello and good time of day, everyone. Welcome to this new MLIR meeting. Today we have Guray, who is here to talk to us about the support that he added for H100 in MLIR. Guray, floor is yours.
Yeah, thanks, Mehdi. Thanks for the introduction. And also thanks having me here and giving this opportunity to discuss my research. And so I work for Google Research. My research interest is in the ML compilers and to exploit GPUs and mainly the Hopper GPU. So that's what I'm going to discuss today. So before I start my talk, I'm going to show the Huang's law. There is a big debate that there's a law or not, because it has to run more than 10 years. But if you look at last 10 years in the GPU performance, it doubles every 2 years, right? I started with the Fermi architecture. It is not even here. And we have a Kepler architecture, is K20. There was FMA instruction there, which was important. And then we got the Pascal architecture. We got the Volt architecture, which is like 6 times faster than Pascal, and it was the game changer. It came with the Tensor core, and it increased the performance a lot. And then we had the A100 Ampere architecture. It even, take the Tensor core beyond, you support more data types, also supported sparsity. And today we have the Hopper. Well, I say we have it if you can get it, but I mean, it exists. And it has like 4,000 times faster than the Kepler, and it was like 4 times faster than the A100. So it is insane performance. Yeah, but the question is, can you really get it, the performance? Well, you can, but in order to get it, you need to, use all the fancy features of the hardware, and that is really hard. So I did a research in the PTX and the Cutlass, and I wanted to understand how these models are evolved. Well, PTX is the virtual instruction set to target NVIDIA, and Cutlass is the cutting-edge matrix multiplication library, open source, and developed by also NVIDIA. Well, during the lifespan on A100, even PTX instruction set significantly increased. We got new instructions and number of page growth, right? So software is very important. And when you look at the Cutlass, the picture is, is even beyond. The Cutlass increased almost 150%. I am showing you here files, number of files and number of lines. Oh, it's a lot, right? Software is really important, and instruction set is really important to get the last bit of the performance. And of course, H100 added more complexity. But in the MLIR or LLVM, did we really keep up? Do we support every aspect of even A100? Or do we have a good support for H100? Well, not much. We have a lot of missing pieces. And the part of my research is completing these pieces. So we are going to discuss today. But as I mentioned, I am interested in the ML model, the machine learning and models, machine learning compilers, and I also wanted to understand what is the challenge for the compiler in a fused ML kernel. And of course, there is a big decision to do fusion or not, but it is another topic that I don't want to discuss it today. It's out of this conversation. But let's say we decided to fusion, and we have a kernel, and inside I have the matrix multiplication, and it generally follows with the element-wise op. So here, what compiler needs to do is a loop tiling. It is introduced. It's older than me. Any compiler can transform. And if you look at the bottom of the code, there is an element-wise op. You need to generate element-wise GPU code gen, which is also introduced, I guess, like 2010 or something. And then, any compiler can do it. And I think computer science solved this problem. So what is the challenge here is to generate the dense matrix multiplication. Because Hopper came last year, and we have no performance portability on everything we did for Ampere. So we need to generate completely new code. And we don't have a compiler solution today. We have some solutions, but they are not perfect. And also there are other problems, how to handle warp specialization. It doesn't fit in our programming model and the compiler code generation. So this is the challenge I am going to tackle in my research. Oh, that's why I am focusing on the Tensor Core of H100 and every aspect to leverage Tensor Core like TMA and using all of these transactional barriers and everything. And I am doing my work in the MLIR compiler because, you know, MLIR is a community driven, it is open source, and it is a good that we can create dialects, high level and low level dialects. And I implemented my work in the NVGPU dialect, which is a high level dialect, and also NVVM dialect, which is very low level dialect that maps to PTX. And also these dialects are, you know, serves as a building blocks of the multiple compilers such as, you know, OpenAI's Triton or like Google's Siri, or if you want to, you know, create your own compiler, you will need to use this dialect. So they are really in the serving block. So it's a good place to work on. And all the work that I'm gonna show here is upstreamed already, and it exists in the MLIR repository. Okay, so let's start with the NVVM dialect. And before I start, I want to answer what is NVVM dialect, if you are not familiar. So it is a dialect that maps to NVPTX intrinsics of LLVM. And for example, you have an op in NVVM. We have ops in MLIR, and it maps one-to-one to NVPTX intrinsics in LLVM. So these intrinsics mostly maps one-to-one to one PTX instruction or like a couple lines of PTX instruction, and you get the PTX instruction that you want. Yeah, but for the Hopper architecture, this is not possible, and because LLVM doesn't have all the intrinsics, and definitely has nothing. It has nothing with the Tensor Core or like TMA. So you have the PTX, and you want to implement the op in NVVM, but LLVM doesn't support that. And to close this gap, my first work was to introduce a new interface, which I called basic PTX builder interface. It generates inline assembly and inline assembly op in LLVM dialect. And in LLVM, it remains as an inline assembly. And you get the PTX instruction you wanted in the end. And NVVM op looks nice. Because I checked the, you know, the cutting edge libraries like Cutlass, it also uses inline assembly because the advanced instructions, I would say, are not exposed in the CUDA. They don't exist in intrinsic, so they also use inline assembly. I think it's a good interim solution. But in the compiler, you know, if you ever generate inline assembly in LLVM or MLIR, you will know that it is so annoying, it is so tedious to write everything, to set all the registers, all the sizes, all the parameters. It's really, really annoying. And if you need to generate a lot of PTXs, that is like a lot of work, right? It's very tedious work. And so that's why this interface comes very handy. It can generate PTX without you writing C++. And what you need to do is to declare this interface in your op, and you create the op. That's what we do in MLIR. I mean, you need to create op anyway. And what you need to do is to give the you know, PTX instruction that you want. And for example, on the screen, I am showing you transactional barrier here and arrive transactional barrier. You can copy paste from Cutlass to, you know, NVVM op, and that is what you need to do. And the interface automatically generates the assembly, inline assembly op. So let me show how does it work. And on the top, there is a MLIR snippet in NVVM. So the op looks normal, op looks nice. And when we run this convert NVVM to LLVM pass, so this pass checks all the op that implements this interface and generates the inline assembly here. So as you can see, the registers are automatically generated, you know, register size. And in this case, all registers are read registers. So there is no, you know, equal for the write. Also, it figures out the register size. That's really cool. So you don't need to do anything. Also, the other nice thing, it supports the predicates. So, you know, you don't have to think about how to support. This is all supported. And when you go to PTX, this is the PTX exactly what you wanted. So it comes really handy. And all the use cases, how useful it is, if you ask. And well, I implemented a lot of things with this builder, right? And I implemented all this split array weight barriers, transactional barriers with it. And I have implemented the election, the leader, that elects the fastest thread in the warp. And I have implemented the warp group level tensor core instructions, WGMMA, and everything related to it, like waiting, committing, and fence. And I have implemented the TMA load store. Well, honestly, I implemented the load, but store is implemented by someone else, which is nice. And I have implemented the prefetch instruction. And now, lastly, I have implemented the matrix store instruction, the SD matrix. Yeah, it is really, really cool and really, really nice to generate PTX and very easy. But of course, the right thing is that LLVM needs to have the intrinsics, so we can, use the intrinsics without generating the inline assembly. That is the right way. But it is the interface is still useful because the ops can remain the same, and we can change the lowering when LLVM has the intrinsics. And even beyond, I mean, even if LLVM has the intrinsics, this interface is still very handy because you might want to generate the blob of PTX. You did some ninja work there. It's like very fast, like small PTX blob. And with this interface, you can easily generate it, like without typing any C++. So I think it is beneficial for MLIR and in many aspects. Okay, now let's...
One question here, Guray. Yeah. Can I go ahead? Okay.
Yeah, of course.
Can you talk a bit about this predicated opcode, and how does it interact when in the same op, for example, we have both intrinsics and the PTX builder support? Yeah, I think that this itself is an op. I think in the actual code we have supported as intrinsic as well, right? So is it like they have to be mutually exclusive, or let's say if I have this inline ASM flow in the same thing, can I add a support for intrinsic, let's say when it is available?
Yes, exactly. Well, it's a very good question. And I needed to support this case exactly for the CP async, like LDG SDS instruction in the SAS, because some of it exists as an intrinsics and some of it didn't exist. Like I think it's a zero field, the padding one didn't exist. So in the interface, like I have a method, and then you can tell that, hey, for this case, use the intrinsics, and this is the intrinsics, and for this case, you can use the inline assembly. Yes, so mixing is possible. You can mix intrinsics and then PTX.
Okay.
I hope I answered it.
Yes. Okay, I haven't played with this much, but so in that case, let's say if I want to use the intrinsic flow, what happens to the predicate argument that's coming in the op, actually in the first box that you have on top here?
That's okay. I missed this one. Yes, that's another good question too. I think LLVM, I mean, last time I checked LLVM, which is like a couple months ago, there was no predicate support in LLVM intrinsics. But I saw another PR that is trying to introduce the predicates. So yeah, nothing happens to predicates. I think I need to, give a verifier error there that predicates are not supported when there is LLVM intrinsic.
Okay. Yeah, that's what my understanding was. So I wanted to just cross-verify with you. So, okay, makes sense. Thank you.
Yeah, good point. Yeah, thank you. Okay. Okay, let's continue with the NVGPU dialect, because NVVM dialect is very important, is the building block, but it's mostly like mechanical translation and to PTX. So let me try to answer first. What is NVGPU dialect? Here I put the official definition of the dialect from MLIR webpage. Also, I put the RFC and introducing NVGPU dialect. I mean, too long, don't read, I can tell you. So it is a dialect it's a bridge between high-level dialects, like, we have GPU vector, or we have another dialects like Linux, and to low-level LLVM or NVVM dialect. So it is a dialect that we can hide all the complexity of generating NVVM in NVGPU, that we can, we can put some, understandable and readable and ops here that user can easily read, but without knowing what happens, in the behind. So let me give you example. I have implemented the warp group MMA op. And, when you look at the op here, I am showing, in the NVGPU dialect. When you look at the op, it is single op, and you can easily understand, what this op does. It is doing MMA with warp group, and it has 2 input matrices and then accumulator matrix. And the size is 128 by 128 by 64. It's very clear. But also I put the generated PTX code. That's insane, right? You need there are many registers there. You split the loop M, and also these instructions run asynchronously. So you need to group them and then launch them, and in the end you need to wait them. It's very complex. Also, you need to select the size of the instruction. That is another complexity. Other thing is, this WGMMA works with the descriptors, and somebody needs to increase these descriptors. This is also complexity. Like you really want to hide all of these things in NVGPU dialect. And so user can target NVGPU, and you can optimize NVGPU dialect and to generate better PTX. But here is a good support to do high level ops. So what I have implemented, so far 3 different features. And first feature is the barrier, M-barrier, high-level M-barrier ops. And another one is the high-level like TMA ops. And the last one is the high-level warp group ops. Well, there is typo here. What is warp group? And so let me explain all of them with an example. Let's start with the arrive at the barriers. So I have 7 ops. And let's start with the create one. In the create one, you can create the M-barriers. In this case, you can create, for example, 3 M-barriers. So this is the high level. And you can create as much as you want, as long as the number of barriers are constant so far. And you don't need to worry about where these barriers are created. We generate in the shared memory, but you don't need to worry about it. And then you can initialize them, and you can access each barrier. So this creates a barrier group, and you can access each barrier with just like you're accessing an array and with the ID. And you can initialize them also. You can also use predicate to initialize them. And then eventually you want to use them, right? So you can use them in a loop, and you can use them, you can weight them, you can set the, TX count. And in the loop, you can calculate the ID for the barriers, and then you can iterate over the barriers in the loop. So that is, I think that's really nice. And that is actually very important to do in the multi-stage matrix multiplication. Okay, and another feature is the Tensor Memory Accelerator.
One question, Guray.
Yes.
On the previous slide. So in the NVVM dialect, most of these ops, we have kind of explicitly supported them for the generic address and the shared address, right? So each of them have like a pair and implementation, right? So
yes,
is that kind of carried over in the NVGPU dialect also, or it's not carried? Or if it is not carried, then what's the motivation, or how do you decide like which way to go?
It is a good question. So the reason that we have shared and generic address in generic ops in NVVM, because the NVPTX instruction is designed in that way. And so I created one op per each, per each intrinsics, because that was the design of NVVM, I think. And but in NVGPU, we have the address space, right? So there is an address space, and if there is an address space, you can use the address space in the create, you can use the address space in the init initialization. So with the address space, we can figure out which NVVM op we need to generate.
Okay, got it.
Create, there is no address space. I also only create in shared memory right now. But in the other ops, if there is address space, it goes to address space 3, it goes to shared memory, otherwise it goes to generic address.
Okay, I got the answer from the question. Thank you.
Yeah, it's a good question. I mean, this is also one thing that we can hide the complexity of it. We have the one op instead of having two, so NVGPU serves nicely in this case.
Yeah.
Okay, so let's continue with the Tensor Memory Accelerator engine. There's the TMA engine, and I will give you the quick introduction, like what is it? I'm not going to go to all the detail. It is an engine in the hardware that can load and store data asynchronously without you using threads. Previously in H100, you could still load data asynchronously, but you need to use the threads. And with TMA, you don't have to. It does everything asynchronously, by engine itself. You don't have to waste threads. You don't have to waste registers, which is really cool. And to use it, but it has two parts, and one part is on the host where you need to call the CUDA driver, and another part is on the device where you need to do, the load and store instructions. So to support this, I don't have like fully support, but I have some support, and we can definitely extend it. And for now, I have implemented 3 new ops for that. Also on the top of the slide, so I am showing you the anatomy of the matmul. So we use this TMA in the prologue section of the matmul, and in the later I will also explain main loop and the epilogue later. So in the prologue, you fetch the data using the TMA. That is the prologue of the kernel. And the first of the create descriptor one, you need to execute on the host. You need to write on the host. And I have also created a tensor map descriptor. So in this descriptor, you can see the type. It's a type. So you can see the size, the box size, and you can see the CVSLink that you want to get. And this CVSLink is 1-to-1 that the driver support. You can have, I think, 32 or 64, 128. Here is 128. And you can also set the L2, caching, promotion. You can set the padding. In this case is 0. I think it's by default 0. Or you can set the interleaving, like everything is in the descriptor. And when you call, when you have this NVGPU up, it's, if you do the lowering, and it is going to generate the runtime call. In MLIR, we have small CUDA runtime, and that calls the CUDA driver. So it returns the tensor map. And the complexity is hidden again. And now another op is the prefetching the descriptor. So now we launched the GPU kernel, and here is the GPU launched where you launch the kernel. And in the step 2, I am initializing the barrier. It's not we need to initialize for the TMA. So this is the op. Like in the step 3, I am prefetching this descriptor to L1 cache, because this descriptor is sent by in this descriptor is sent by like memcopy. So I have memcopy. I didn't write it, but I have memcopy before the GPU launch. So I prefetch it. And the last op is the TMA async load. So it's here. You can also use the predication, and you can use the descriptor, and you can also set the coordinates where you want to load, also the M barrier, and then you can request the loading tile. In this case, 128 by 64, using the TMA, and this will load asynchronously. And in the step 5, you set the TX count, and then step 6, you can eventually, your all threads can eventually wait. Well, there's a simple example how to use TMA. And okay, here's, I also put the generated PTX. I am not gonna go all the details in this talk and of the PTX, but I want to put it because I will give the slide. So, I mean, you can read it afterwards.
One simple question, Guray. The previous example that you showed, is that part of a unit test or something that we have for the NVGPU dialect somewhere?
Oh yeah, I have a code gen test, lowering test, plus I have an integration test that
integration test. Yes.
The integration test. Yeah, you can run end to end.
Okay, thanks. Yeah.
And the last feature I implemented the warp group MMA and warp group matrix multiplication. So we use in the main loop, to use to multiply the matrix. And I came up with 4 new ops. And the first op is the initializing accumulator. And so when you call this op before the loop, and it creates registers, how many registers it needs, and then it sets registers by 0. You don't have the accumulator matrix here. And I mean, for example, for this case, I think it generates 128 registers. You don't need to know anything about it, and it does. So it does. That is, really useful. Otherwise, generating all these registers here really, it bloats the code. And then we have a loop, SCF4 here. So this loop is basically the K loop. It iterates. You can think about the K loop. It iterates over the K. And another instruction inside the loop is the generate descriptor. Because if you want to use WGMMA with TMA, and you need to generate a descriptor, and the descriptor is very complex. It is 64 bits, and each bit means something. And I put what they means. And it is also annoying doing all the shifts and cuts of the integers. And this ops does that. What you need to give is the base address, also the descriptor, the TMA descriptor you generated on the host. And yeah, this is the complexity it hides. And the last one is, it's the third one is the MMA. So this does the matrix multiplication. And I showed the PTX instructions like earlier in my slide. It generates like many PTX. It selects the size of the WGMMA, and it groups them, it launches them asynchronously, and etc. And the size is here again 128 by 128 by 64. And then you are done with the loop, right? So now you use the tensor core perfectly, and you finish the loop. And after you're done with the loop, your all results are in the registers. So these registers are fragmented, and one thread doesn't own the whole matrix, or one thread doesn't own the whole row or like column or anything. It's very fragmented. And the fragmentation is, you can check the fragmentation in the PTX document. So to hide this copying from fragmented registers to shared memory or global memory wherever you want, I created another op. That takes this register, that takes the registers from the threads and then copies the correct place in the shared memory or global memory, like wherever you prefer. And currently, this op is implemented using regular, like vectorized shared memory load and stores. But in the future, we have a SD matrix op, SD matrix instruction in PTX. We can optimize this op by leveraging this instruction. And the user code is going to remain the same, right? So the whole main loop is going to remain the same. We can do the optimization in NVGPU. So I think it's really, so this part is also really nice. Okay, and so let me show some benchmarks. Yes.
On the previous slide, on the second item here, the generate descriptor. So I believe all this bit shifting and the whole work of constructing that whatever value, 32-bit or 64-bit value, I believe we are doing here. So when it gets lowered down into the NVVM dialect, it just goes as that value, like an I64 or something like that. That's what is happening today.
Yeah, exactly. That is what is happening today. It does shifting, and if it's compile time constant, all these values are compile time constant. It shifts in the compile time. So eventually it goes I64. Yes.
Okay. And this descriptor generation code is not like again replicated at the NVVM dialect today, right? We have this only here.
Yeah, we have this only here. I mean, actually I cannot duplicate in the NVVM dialect because it doesn't correspond to any NVPTX instruction, right? That's why NVGPU is really cool. We can do other things than in intrinsics.
Okay, makes sense. Yeah, thanks.
Yeah, sure. Okay, so the benchmarks. Well, I don't have a lot of benchmarks, so I did write a multi-stage kernel and in NVGPU dialect, and I used H100. I have only one access to H100, which is PCI Express. It has lowest memory bandwidth, so if you have numbers from other H100, be careful. Maybe they are not the same GPU. I took one size and one square size, like 4K by 4K by 4K, and I took the F16 data type, which is the easiest one, and result is F13. And so in this kernel, I used every feature that I introduced earlier. I used TMA and I used WGMMA, and for the matmul, and there is no split K, and I used 128 swizzling with the TMA. Also, I used the software pipeline, the maximum software pipeline stages. I think is 7 here. Yeah, my tile size is 128 by 128 by 128. I forgot to put here. And then when I implemented that, the performance wasn't so great. I got like around 330 teraflop, and which is not didn't meet my expectations. So I started optimizing, and I tried the simple things. The first thing was the setting the short pointer flag, and that demotes the address, that demotes 32 bits address space for the shared memory and constant memory. And it gave me a little bit performance bump, and it used to give more, but I realized in this kernel, there is no address arithmetic. Everything is done by TMA. So there is not much arithmetic going on, or it is not surprising that I didn't get much performance. And another optimization I tried the L2 cache hint of the TMA instruction, and it didn't give me much. Actually, it didn't give me anything. And in optimization 3, I set it the launch bounds. In this case, I launch a one warp group 128 threads, and so it does better register allocations, the PTX-AS compiler, when you set this flag, but it didn't do much in this case. And in the optimization 4, I tried to set no alias on every kernel parameters, and also nothing happened. Well, because I think my parameters are the TMA descriptor, so it is not much happening there. The optimization 5 gave me actually a lot of bump, which is surprising, and I started using the predicates. And so in the main loop, I do the matrix multiplication, plus I keep feeding the stages, right? I keep feeding the TMA, and I used to do this with the if statement earlier, and I think I didn't see any synchronization in the PTX, but I think when I look at the SAS, there was some synchronization there, and it was killing the performance. I didn't look extremely carefully, but after I changed the predicates, I get rid of the if statement, and I run the TMA instruction with predication, and it actually gave me like nice performance bump. Oh, it was nice. And the optimization 6, I interleaved the epilogue, which means in the epilogue, I used to copy all the data to shared memory first, and then synchronize, and then copy from there to global memory. So that was not very optimal. So what I did was I copied some chunk of the data to shared memory and then global memory, and I did it again for the remaining registers. But I did it manually. There was no NVGPU op yet for that. But it gave me a little bit performance, I think like 10, 20 teraflop. And the last optimization is I located the TMA descriptors to L1 cache with the prefetch tensor map. This wasn't super helpful. In the end, I think I got around like 400, 410, 420 teraflops. So I wanted to compare my performance with other, state-of-art compilers, or like NVIDIA Kublas or like Cutlass. So I took the OpenAI Triton and the old one, and that generates the A100 style code. So it didn't perform well. And I took the Kublas, but I didn't do the benchmark by myself for the OpenAI Triton and Kublas. It is done my colleague here. Yeah, but cuBLAS, for example, is also performed like similar to like the upstream MLIR today. So this work I am introducing. And the Triton, OpenAI Triton has also H100 now, and I use, I think, their beta version. It has TMA and WGMMA as like probably similar thing. And they all get 420 teraflops. And when we run Cutlass, so Cutlass doesn't have a heuristic, right? It runs all of the algorithms and you need to select the fastest one. So I think in this case, the fastest one was the ping pong with the warp specialization, ping pong with the, epilogue also with TMA. And so it is the best one, best performing one. Well, so the result is here. Well, are we generating bad code? Well, no, we are not actually generating the bad code. And so the reason we are off from peak performance in the MLIR, and we still need to, implement more features that Hopper has. So let me show what are they. And if you look at the Cutlass, which is the matrix multiplication library from NVIDIA, you will see 5 algorithms for the matmul. And in these 5 algorithms, the second one is the kernel TMA, which I implemented. I think cuBLAS is using in this case, or like OpenAI Triton was also using the kernel TMA. So that's why the performances are very similar. So this is the performance of this algorithm. And the other algorithms like warp specialization or the warp specialization with CTA clusters, they are going to optimize the prologue and epilogue side, and they are going to improve the performance. And to get more performance, yes, we need more work to do it. So the answer is, yeah, we don't generate bad code. We generate a good code for this algorithm, but algorithm ends, it performs only as much. Yeah, okay. So this is the last slide of my talk, and let me summarize everything. So here I'm trying to target, Tensor Core of H100, and I am doing an MLIR compiler. It is nice. It has dialects where we can abstract away many things, and ventors like NVIDIA has a great history of the active contributions. And yeah, all work I did is upstream, and I keep improving the work. I keep improving the support. Yeah, thank you so much. Yeah, let's see. Yeah, that's all from me. I think if you have any questions, like feel free to ask, or you can write also in the chat. I opened my chat box.
Well, thank you, Guray. It was impressive results at the end, and looks like a lot of work went into adding all those primitives and those abstraction into MLIR to be able to target those complex accelerators. Yeah, let's move on to question. There are like some message in the chat.
So Guray, I have one question about the TMA, the asynchronous copy of a tensor. So you wait for the data to arrive by a barrier, or is there a more accurate event-based waiting?
Yeah. Good question. So let me pull my slides about that. Which one? Yeah, I think this one is good. So TMA works. You need to use TMA with this asynchronous barriers, and you fetch the data. You submit in data request, and you give the descriptor. You give the coordinates where you want to load the data, and you also give the barrier. And then in step 5, so I think this is the answer of your question. You say, this barrier needs to wait this amount of data. In this case, is the size of 128 by 64, and it is F16 type. And so this byte, it needs to wait. And you set the barrier. And then after that, you do some another work. In the step 6, you wait this barrier. So
okay, so MVAR is actually the token that you're passing between the launch and the wait.
Yeah.
Got it.
Sure.
Nice work.
Thank you.
Hi, thanks for the talk. I really enjoyed it. So I joined late, so you might have already covered this, but do you do any optimization within NVGPU on these instructions, or is it kind of just like a one-to-one lowering to BTX or BTX macros?
I think right now is one-to-one, is not one-to-one lowering, is one-to-many lowering. Like I show here, let's go to beginning. Yeah, let's go to this slide. Like for example, in NVGPU, we have like one op, the work group MMA op, but it generates many PTX or like many NVVM dialects. So there is no like compiler magic. Everything needs to be exist in the NVGPU op, so we can generate many ops from that. I don't do optimization yet, but we might.
Isn't there like one optimization about buyer that has been implemented recently? Like eliminating redundant buyers or something like that. Do you remember this one?
Yeah, there is that one, but it is not in the NVGPU dialect. It is I think general pass that eliminates redundant barriers, duplicate barriers or something.
Thank you, Guray. It was very helpful.
Yeah, sure, happy to help.
The pass I was referring to, I think, was the GPU eliminate buyer, but it works at the GPU dialect level. So it's not specific to the NVGPU itself, indeed.
Yeah, we don't have barrier in the NVGPU dialect yet. I mean, apart from the M barrier.
Yep.
Yeah. In the chat, Renato says, can you share the slides later? Yeah, I'm going to share the slides. Yes, for sure.
Yeah, I'm posting recording on slides online later today.
Mm-hmm.
As with every talk, there will be on our website and as well on Discourse. So if you track the Discourse thread, you're gonna have the slides on the recording later today. So by the way, Guray, you need to send the slides to me after the talk so I can put them online. So there was this question about optimization, and right now you're not doing analysis or optimization, but what potential do you see for optimization at the NVGPU dialect or the NVVM dialect? Have you thought about it, or is like LLVM good enough? How do you see that?
No, we can do some optimizations. Can't say, but I can say actually I have the exact slice I wanted. So for example, here, in warp group MMA op, we generate multiple WGMMA to complete the given shape. And WGMMA op has different, shapes. And the size of the shape can be, select by the compiler, if it's possible. It's depending on. If you increase the shape, you will use more registers. If you reduce the shape, you can use more registers. So this is the selection that we can do in NVGPU dialect.
So basically, you say you would tile so they can spread this across the different work groups or different threads Wouldn't it be easier to do this at NVGPU level, where you actually split your warp group into multiple MMAs?
Or the splitting work to multiple warp group, I don't think I can do in the NVGPU. It is like too complex for that. And I think it's better to do these things like before generating NVGPU. And but what I was saying, so here, you know, there is the size of the op 64 by 128 by 16. And so you can change the size. And when you change the size, yeah, one WGMMA instruction will do larger or like smaller matmul. And then you might need to generate, you know, more than 8 or like less than 8 and WGMMA, and it can, you know, work faster or slower. This kind of optimizations we can do.
Right, but you would need to fit into the register, right? So if you
Yeah,
have a
you need-
larger, yeah, okay. So there will be like one optimal for each type of hardware, type of op, right? It's not something like you can try multiple things. You kind of know statically, well, this hardware has this number of registers with this number of groups and this number of threads, so this is the optimal number of MMAs that I can issue with these sizes, right?
Yeah, exactly. I mean, this optimization is like extremely target specific. I mean, it is actually the very architecture specific. It's
Yeah.
H100 is one thing. Hey, you know, something else. RTX something is going to be another thing.
Mm-hmm.
And wouldn't it be also like kernel specific? I can imagine that if you already are using registers or something else kernel, then your occupancy may depend.
Yeah.
Whether you cross a threshold, right? So
exactly right. If you have a lot of fused ops, so you will have more registers, and then you want to do different things.
Mm-hmm.
Okay, so in the chat, and there is one question. What are the next steps to achieving parity with NVIDIA Cutlass? Yeah, so let me go take my slides. Well, to get the parity first, you know, we need to implement the CTA cluster feature in NVVM and NVGPU dialect, and because this is the remaining feature. And then Cutlass has warp specialization, and also Cutlass has warp specialization with the CTA cluster. So if we can implement this, you know, warp specialized kernel, then we can have the same performance as Cutlass. But again, I am doing all the work writing everything in the NVGPU dialect, so I don't have any transformation to, you know, from high level lean out the NVGPU dialect yet. So there's gonna be another future work. So there is another question in the chat. Is the pipeline used for generation the performance result in this talk included somewhere upstream? Well, not yet, although some yes. And I have, I think, 2 integration tests that does matrix multiplication with the 2 pipeline stages. And yeah, that works end to end. And I can also upstream the benchmark that I did. The reason I didn't do it, this is like too large to be a integration test. It actually, you know, takes time and requires, you know, some computation time. I am not sure it makes sense to put an integration test, but maybe I can put as a, you know, code gen test for it if people want.
is there like, can you, like, maybe you can put the code with a small size, you know? It's like the integration
I have
test.
the small size. I have the small size one, yeah, already.
Yeah. And maybe you can command out the, you know, or maybe make the size a parameter so that, you know, people can increase the size to run performance benchmark.
Yeah, we can do this. I can reduce the I can reduce the M and N loops and then keep the K loops, so we can still have the software pipeline stages and everything done on the one thread block. So if someone wants, you can increase. Yeah, that's a good idea, actually. I will do that.
Well, thanks again, Guray, for your work. I think if there are no more questions, we can leave it there for today. Thanks everyone for attending, and see you next time.
Thank you.
Thank you so much.
Thanks. Bye.